For now, let's crack on with these. So I've got it left off. Well, I got it started from where we left off last time. This one was pulled from another VCAR exam, so this will definitely be quite relevant, or at least as relevant as possible. Let's have a look. So we've got two separate functions, an exponential and a logarithm. We can see there's going to be some bound area between them, simply because they have been shaded in such a way. They're given a bit of a background for it, so if we do have to do anything with distance or area, we'll be using the kilometres and kilometres squared, respectively, because that is the unit provided. So far, first question, fairly straightforward, just evaluating the integral. Not much to be said there. This is a tech active thing, so we're just going to go ahead and do, well, firstly define the function f of x as e to the power of x, and then just do that integral. I don't think there's much to talk about there.
Oh, and one more thing, I finally got my CAS back.
Yeah, I imagine, because you've just finished the SAC, yeah?
Yeah, I got it back today.
Just today. Oh yeah, because that was your
Yeah.
first math methods class for the week.
Um. No.
Monday had it, and they just kept it anyway.
Yeah.
Sure. But okay, cool. So fx e to the power of x, and then yeah, just evaluate that integral. That is not the integral button. This one is. -2 to 0. F of x dx. This ended up being a one marker. The older exams used to subtotal all the marks in different ways. So it'll subtotal it like that. You can see at the bottom that this is meant to be a one marker, so all we're going to do is give the answer. That's pretty much it. Double I is where it might get a bit more interesting. Hence or otherwise, find the area bound by G, the x and y axes, and the line y equals -2. So we got those all written out. Graph of G, that's going to be that one. X and y axis, so that's going to be now looking at this sort of area. And the line y equals -2, we're truncating that off. So it's going to be specifically that portion of the shaded bit here. Hence or otherwise finding that.
Do we just oh wait, no. So integration, finding the area bounded by two curves
Yeah.
or two graphs.
What are the two graphs that you're looking to?
So that's y equals to -2 and g of x.
Yeah, that is one way of doing it, absolutely. You can take these as two separate functions, and you can do a top take bottom of it. So you'd be integrating from 0 to 1 of top being g, bottom being y equals -2, and that would get you that area. That should do it. So let's try that. G of x equals natural log of x. Shift plus, so we're doing from 0 to 1 because that's the domain. Then it's top take bottom, so it's going to be g minus -2. So g of x minus -2. What did I do wrong there? Top take bottom. Why is that not? No, I think I know what's up there, because for a certain portion of this, the top is not actually G because it clips at the x-axis here.
Yeah.
So doing top take bottom over that domain, you're kind of doing this bit, and then, well, that's at least if you were doing top take bottom with those functions, you're getting these bits here.
Okay, so we can separate the functions.
Yep.
We can split the integral, and we can use, instead of g of x for 0 to whatever domain.
So like g of x is in, you're going to do like this portion for g?
Yeah.
Yeah,
And
so stopping it wherever it equals negative
yeah.
2, sure.
So that's the intersection. And between 0 and that intersection, you can find the area bounded by y equals to 0 and y equals to negative 2.
Yeah, yeah, so
I mean,
splitting it up that
that's
way
fairly.
would
I
work.
mean, we don't need to do the integration, it's just a rectangle.
It is just a rectangle, yeah. That will work. That sounds like it'll work now, because we are clipping it at the x-axis. I will point out, this one also ends up being a 1 marker. We'll do this approach just to prove it works, but then I'll also show you there's this keyword hence or otherwise that should be trying to make things a bit easier. So while I plug away at that and get some of those sorted, have a think about what the other possible solution to this would have been. So, okay, finding that, we need to figure out where does g equal negative 2 to get our x value. So g of x equals negative 2 comma x. That's going to get us that as our integral bound. So from there, we're going to do from 0 to e to the minus 2, and that's just going to be the area under negative 2. Yes. And then same sort of thing, but this time this one's going to clip at 1, this one's going to be the e to the minus 2, and the function is now g of x. Then it's going to be the addition between these two things. And that's going to get us e to the minus 2 minus 1.
And okay, I think I figured it out. So you can integrate. You can find the integration. We can find the area of the graph of f of x. So under from negative 2 to 0.
From negative 2 to 0? Yeah.
Yeah.
And why does that give us what we want?
Because it's already given.
Yeah, so as in like, what is it about this that gives us that?
Oh, they are inverses.
They're inverses, exactly. You got basic exponential and the equivalent logarithm for it. Because they're inverses, rather than trying to find this split of values, we can instead find this one here. And you can even see just by me sort of highlighting the two together, they look like they're equivalent areas, and they are, because they are inverse pairs. Nice. So yeah, always looking at that hence or otherwise, it's worth paying attention and try to think about what is it about the previous questions that are useful for what we just did. Okay, and then total area of the shaded region. So shaded region now being not just this piece, but also all of this as well. Can I get that all on the same screen? Yeah, there we go. Total area shaded region. That's our shaded region.
Can we use the area bounded by two curves for this?
Can we bound by two curves? Almost. There's one thing that's a bit stopping it, and that's this little cutoff here. Bound between two curves, you could probably do this section of the slither, but then you'd have to find this plus this little bit here.
Yeah.
That's the right idea, essentially, trying to figure out, well, okay, there's two curves that are binding it. There's actually a third. So you could, because it would just be a matter of doing area bound between two curves twice. Right, you do top take bottom for this portion, f over y equals -2, and then top take bottom for this portion, so f over g. That would work. The other alternative would be grabbing, because you already know what this portion is already, so really all we got to do is figure out this bit here, and figuring out that bit there and then just adding it to this seems a lot more, a lot simpler to go ahead and do. If we just wanted this, what would we do? Because we got this bottom bit already. And we can see, based on the shaded area, there's actually only one curve that this encompasses, and it's just f, because it stops at x equals 1, which is right before g of x even comes into play. So this portion here is just going to be the area under f from 0 to 1. So we can do exactly that. 0 to 1 of f.
Can we just do -2 to 1?
-2 to 1. Yeah, -2 to 1 should also work, but you just obviously wouldn't want to add it to that then. What I said was you take this and add it to this one, but what you've done is also fine, I think, just going from -2 to 1, because that already encompasses this portion. Yeah, that'll be faster. Let's do that. -2 to 1 of f, and that's actually literally it. A minus e to the -2. Perfect. One of the things that was a bit sketchy about, just to bring back to this bit here, a little bit sketchy about doing the integral stuff here, is that because we're no longer doing, or at least the approach that we did, we weren't doing bound between two curves, what we were actually getting was the negative area, since it's below the x-axis. So when we find, we're trying to do this question, if we were to do it this way of splitting it up into two little sections and adding them up together, making sure that you then negate that one more time to flip it back to be positive. We've circumvented that entirely by just focusing on the f, because it's already above the x-axis. But yeah, each of those were 1 markers, so in summary, well, this one, really nothing to talk about there. That's just the integral. Hence or otherwise, that required us to understand the inverse relationship between the two. And then total area of the shaded region, you had a couple of ways to do that. One was to, again, just use the inverse relationship and just find that area once again. And the other was to instead take this thing that you already know and then just add it to this bit that you don't know yet. Okay, this one's extending fairly lengthily, so what I'll do is I'll grab a copy of these in the chat so you guys can follow along if you guys want to scroll back and have a look at the pictures. So that'll be downloading shortly. In the meanwhile, let's have a read. Mining engineer decides a better site for the mine is the region bound by the graph of G and a new function, a new logarithm. Find in terms of A the x-coordinates between the two functions G and K. So find where G and K intersect is all that's asking. Find the x-coordinates of the points of intersection between G and K. So one thing you could potentially do here would be to graph both of those functions. So g of x was the logarithm, and k of x is also going to be a logarithm. So if we get a couple of graphs going on, one of them will need a slider to do it, but we can at least get an image of what's likely to be the case. K of x, slider, yes. And what are my restrictions on a? So a has to be a positive real number. Okay. Which it currently is. And we can see, at least for a equals 1, there's going to be no intersections there. For a equals 2, we might have just found the tangent. It does look like it's tangential there, but it might not be. And then we can see as a increases, we're shifting more and more right and actually creating more and more bound area. So let's just leave it there at a equals 5 for now, just for a quick demo of what the possible outcomes are going to be. How do we find intersections between any two graphs?
Set them equal to each other.
Set them equal to each other, absolutely. So if I simply go ahead and do g equals k for that particular value of a, I'm going to get a couple of solutions. Now, I want to have this generic for all a because it says find in terms of a. So what I'm going to do is kill the slider that I just created for a, delete the variable, and do the exact same thing again. That's going to give us a couple of possibilities there, of which looks kind of complicated. So let's strip off the domain stuff just for now, just so we can at least have a look and see what x values were created. So those are our outcomes there. It's essentially a quadratic formula there. It's going to be the plus minus the square root of that term divided by 2. Right, if you distribute that negative through, you'll have that go back to positive a, so both of them have plus a plus a. The only difference is going to be whether the root is negative or positive. We do also have to worry a little bit about whether or not both of these are defined as part of our domain. That's where you might start looking at this sort of stuff here. So as long as this is true, so essentially as long as the square root is between plus minus a, and again as long as the square root is between plus and minus a. So, and the reason that's there is because if we remember from our graph, certain values of a would cause this not to have any solutions at all. The question then becomes, do we actually have to restrict anything further? Like, do we have solutions here that we should not have? We've got a plus minus root. Do we have to kill one of those or not? I would urge you to think in terms of domain here. So changing a value does not necessarily, it impacts domain a little bit in the sense that it tells you the asymptote of the k of x graph. So have an exploration if you have your CAS and just see as you're choosing a values, is there ever a point where the intersections are outside of the domain that we have? Have a think about that. Like, to give you an example, perhaps, for a equals 5, you have an asymptote here at x equals 5, but the solutions are between something a little bit less than 5 and something a little bit bigger than 0. So in this case, both the positive and negative root are defined, right? There is no solution that exists outside of x equals 5 for this one. For a equals 4, we're going to have a similar story. A equals 4, we have an asymptote at 4, but because it's curving this way, wherever it's going to intersect is going to be left of that asymptote, never right of it. So both this solution and again this solution are valid. Based on at least these two investigations, is there ever going to be a time or a value of a which is going to cause there to have only one of those roots be valid? Or can we just have both?
I think we can have both.
We can have both, absolutely. Doesn't matter how far right you shove this thing, because this curves to the left, wherever it touches this curve is going to be part of the domain. What do we do about a being, well, there being no solutions out here? There's nothing actually bothering, there's no real bother there, because what you get is the roots are still possibilities, but they just become undefined, right? You get imaginary solutions from it. That's not necessarily a reason to kill the answer. But yes, so that means that we will give our answers. You can give it the most succinct way as just saying the plus minus root plus a, or you can give what the CADs are given, as long as you strip this stuff. You don't really need this bit here. It's implied that your a already has, there's already implied domain for a in there. In fact, it looks like we'll be exploring that in the next one anyway. Hence, find the set of values of a for which there are two distinct points of intersection. We explored that a little bit, I think, actually. We might have even found the breakpoint. But we wouldn't necessarily rely on the graphing tool. It can be a bit hard to say whether we found that breakpoint. And by breakpoint, I mean when we had a equals 2, it looks like it's tangent there. And that would be, one distinct point of intersection rather than two distinct points of intersection. It looks pretty tangent, so that'll be a nice little starting point to think about. But we'd want to be a little bit more sure, mathematically speaking, because maybe when you're working with these kinds of graphs, perhaps it's more like 2.001, and then you kind of shit out of luck there. You'd have some, e to the power of something in there, perhaps. There's something in the math that'll validate whether or not a equals 2 is a cutoff point. So to explore a little bit more, what it's effectively asking is, what are all the values of a for which we have two possible solutions? So for instance, a equals 1, there's no solutions. It doesn't cut at all. They don't touch each other. For a equals 2, it looks tangent, so just by looking at it, we can kind of assume that's going to be one solution. We'd want to prove that, but just for hypothetically, we can say that it's one solution there. And then we can see that as a increases beyond that point, there's definitely two solutions. And you can imagine shooting a as far right as possible, you're only ever going to have two solutions from that point onwards. So our goal is to figure out where's the breakpoint. And 2's looking like a pretty good idea. We just got to have a little bit better of a reason other than just the look, because looks can be a little bit deceiving when you're working with like irrational numbers like e's and pi's. The other hint will be, it says hence. So our previous answer in part I is likely to be something that's going to matter here. I made a comparison between this set of solutions and the quadratic formula, how we had the plus minus square root. Two solutions is also a thing we do for quadratics as well. You know, one solution, two solutions, no solutions.
What about like wait, I think we can try and find values for A for which there's only one solution.
Yes.
Wait, no, yeah. Okay. But how are we gonna do that?
That's a great question. So what we have is the generic formula for the point of intersection on our graph. You know, we have the plus minus root there. That's normally two solutions, right? But if we think about quadratics, there's certain things about quadratics that cause those to give you one solution or even no solutions. What is it that we can apply from quadratics that can help us condense this down into the one solution breakpoint that we're looking for? We're looking for a way that both of these x equals give the exact same answer. Because if they give the exact same answer, that's one solution.
They're intercepts, so have them equal to each other.
Yeah, making them equal to each other. Yeah, that should work. Let me just clear the variable, otherwise we're going to get a bit of a weirdness. Yeah, okay, let's do that. So mini31, solve for these two things equaling each other. Probably should have put a comma A at the start, but oh well. Comma A. Sounds pretty good to me. A equals 2, also supported by our graphing tool as well. We also have A equals -2 there. Do we think that's going to be valid or not? Both the...
No.
Yeah, exactly. It says in the question, A is a positive real number.
Yep.
Cool. So that's one way of doing it. Just doing the make the solutions equal each other, and you know that'll get you the one solution because they are the same solution by drawing that equal sign. The quadratics thing that I was alluding to is discriminant, right? You've got this plus minus square root term in there. As long as the inside of the root, or I guess the root itself, goes to 0, then the roots disappear entirely, and what you end up with is just the bits on the outside. So you could also just solve a squared minus 4 equals 0, which is where you can clearly see the a equals 2 has come from there. Well, a equals plus minus 2, but we're slicing that off. Both approaches are fine, whichever comes to mind in the exam. Yeah, okay, so to recap what was going on there. So in the beginning, they introduce a new function, which now has a in it. They start by asking you to find the point of intersection between g and k. We just think higher level, okay, we got a function called g, we got a function called k, we want to find the intersection between them. How do we do that for any function? Make them equal to each other. That's what got us this bit. It did also put some restrictions on a. That's fine. It just becomes... It's a bit of noise in the thing. It's giving you more information than you need to actually answer part I. Then we had hence find the values of a for which the graphs have 2 distinction points. So keyword hence means we should be trying to use the answer to part I. That was the 2 x intersection points. And yeah, 2 points of intersection. We look at our graph, we see that for certain values of a, we have no solutions, 1 solution, or 2 solutions. So we just want to give all the values for that accordingly. To finalize the answer for double I, it did say find the set of values of a for which there are 2. We just found the breakpoint. So all we would say would be a is an element of 2 to infinity, non-inclusive of the 2. Any questions there? Happy to go back on them as well if you decide to jump in later on. But otherwise, let's have a look at part C. New mine site, graphs of G and K intersect the 2 spots. Cool. Okay, we've already figured out where those might be. The mining operations will exist along the line segment that connects those 2 points. Okay. The graph of K will be such that the x-coordinate of the midpoint of AB is root 2. Okay, righto. So effectively we're drawing a line between our 2 spots, and whatever the midpoint is of that is going to have an x-coordinate of root 2. So to get a mock visual of what that would look like, if I go ahead and chuck in a equals 3 for instance, we are drawing a line connecting this intersection point to that intersection point, and wherever the middle of that should be, which may or may not be on the x-axis. I don't know, it might be a little bit left of it. Point is, whatever the midpoint of that is going to have an x-coordinate of root 2. Actually, perhaps what I should do is draw a draw an actual picture of it rather than do that, because it's a little bit small. So what we're trying to achieve here is as follows. We have root number 1. Oh, not a root, sorry, a logarithm. Logarithm number 1. We have logarithm number 2. They intersect here and here. A line is joined between, so let's just call this A and this B. A line is joined between the 2 of them, and the midpoint of which is going to have the x-coordinate of root 2. Okay, and that was super blurry the whole time. Great. There we go. Readable. That's what we're trying to achieve, and we're trying to figure out what value of A would cause that to happen. 2 marks, so there's a bit of working out to be done here. What could we start to do?
We can start off with the distance formula. So square root of
distance formula.
Square root of the square root of change in x squared plus change in y squared.
So if this one's x1, y1, and this one is x2, y2, then yeah, we're basically doing our Pythag if we're going to get our distance formula. So we could do that. I'm not super sure where that's going to lead to. Do you have any stepping off points from there that you want to do after getting your distance? Like, potentially I'm thinking you could maybe halve whatever you get for your distance formula, but because it's it's just a scalar, it doesn't tell us direction, it's kind of hard to then translate that to x and y coordinates, at least in my estimation. Because like, yeah, let's say you get a distance of like 5 for this whole thing, and halving that gets you 2.5, so you can say, okay, distance from here to here is 2.5, or from here to here is 2.5. It's then hard, or at least I'm not seeing a way where you could then convert that to saying, okay, well if distance from here to here is 2.5, then I should be able to, well no, I guess you could just reshuffle that back into the distance formula, couldn't you? That could work. Get this coordinate, find distance, halve it, and then keep one of these coordinates the same. Nah, it's 2 variables. Bugger. Because I was going to say, well, okay, keep one of these known coordinates the same, have this additional point C that you're trying to find. But having done that, so you got distance, which is known, square root of x1, which is known, x2, which is not known, y1, which is known, and y2, which is not known. So you've still got, like, this is known, 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 unknown, unknown. So unfortunately that's going to end up being, well, maybe not. They got root 2 there. That's the x-coordinate. That looks good. Not what I was going to do, but looks pretty good. Let's see if that works. Okay. So let's have an explore. So those are our two sets of solutions there. Let's get those written down. So we have x equals a plus minus root a squared take 4 over 2. Those are our two x coordinates. The corresponding y coordinates are therefore f of x, where x is these. Or I guess more specifically, what's the function called? It could be k or g, whichever. They'll give you the same thing. Which one do we need to actually use? Shouldn't matter, because you're still going to put a in it either way. So let's just say it's g. So that's going to get us our coordinate pairs from that. Cool. Let's give that a shot. So to get our coordinate pairs, we're going to go g of this one. Ah, shit. 3. Okay. And then the other coordinate pair is the positive. Cool. Now from there, distance formula, so we're trying to, that's just evaluating. So we go, no, it's not a solve, it's an evaluate. So we go square root of x2 take x1, so it's going to be, oh, I didn't know I was going to grab the whole thing. So it's that. Oh, sorry, I just looked up. Yeah, Taha, you got a question?
It's a bit unrelated, but what's the command on the CAS to define the function again?
Menu 1.1. Menu
1.1.
actions define.
Thanks.
Yeah, no worries. So this is x coordinate 1, so it's the difference of them. Yeah, so that take the positive version squared plus f of both of those, or I guess g of both of those squared. So brackets squared of this one take this one. Okay, then we halve that because what we had was the distance between A and B, but we wanted to get the midpoint of it, which would occur halfway along the length. From there, we can now make that as our solve. So we've got, this is our distance that we're trying to equate it to. Then we've got to keep, we've got to keep all of this except we're removing one of the x coordinates for root 2. and leaving the other y coordinate as blank. So, okay, which one are we going to keep? I guess it doesn't really matter. Let's say we're keeping the positive root 1. So we leave this as the variable we're trying to solve for. I didn't count a as a thing. Is this going to have 2 variables in it still? Shit. Let's find out. And this one's going to be... No, we've got to kill the negative root 1. And replace that with the root 2. Solve that for x. I think it's going to maybe fail because I forgot that a is a variable. Yeah, okay. So even just looking at the size of what we created, it's probably going to crash the CAS or make it think a long while. But yeah, that had a lot of merit to it. It really looked like it was going to simplify all the way down to just having one variable. I just neglected the fact that we wanted 0 variables in there actually, because a we're trying to solve for, and a is in all of these. But I really like the idea. In fact, we did get a solution. We got x equals that in terms of a, but we need just a. So cool little sequence. Let's think of something else we could potentially do then. So if distance formula is off the table, what are we left with? Well, the only way to reliably, or the most reliable way to get the straight line related information related to x and y coordinates is to actually just find the equation of what this line would be. So if we can figure out the equation of the line, we can know a whole bunch about it. Alternatively, we're actually told this is the midpoint already. The midpoint has to be root 2, or at least the x-coordinate of the midpoint has to be root 2. So rather than going through the more heavyweight solution of getting the full equation, we might be able to get by on just using the x-coordinates and just doing the midpoint formula on those and making those equal to root 2. Because if we look at those, let me just grab another copy of this solve, those already only have a in them, as is. And so if we just do the midpoint between them, which is just going to be a on 2, because the plus minus root, they're equidistant from each other. But just to demonstrate that, what you would have to do is, I'll first get rid of the solve. Then for midpoint formula, it's the addition of the 2 points and then dividing that whole result by 2. So that's going to get the a on 2. Again, we know this from quadratics, right? It's plus minus root, which gives the variance between them, and they're centered at the axis of symmetry. So if we now have a over 2 as the midpoint, but we also know that should be root 2, finally we're going to have a over 2 equals root 2, comma a, and that's going to finally get us our valid solution of 2 root 2 there. So, I'm even looking at the exam report on this. Apparently a decent number of people use the distance formula to try and get there. 82% fail rate on this. Makes a lot of sense, especially for those who would go down a distance formula route, because you'd be, especially if you got all the way that we did, you'd be crying and be like, oh shit, I got that far and I didn't get it. Damn. But yeah, so we're doing a similar sort of thing, but rather than doing distance, we're going straight to the midpoint and cutting out a lot of the stuff that was irrelevant to it. Any questions on any of that? We spent quite a while on that one, so I'm hoping that's all tracking. If not, happy to re-explain it from the start. Okay, let's move on then. If you're in the middle of typing something, I'll have a look at it as well. Don't worry. Happy to go back. Okay, this one, I don't know if this was... I know Northern Hemisphere exams tend to do this sort of thing where they put pictures in colour. It might be VCAR. Anyway, we've got a disease given by a... Well, actually, the derivative. Yeah, we got the derivative function, the rate at which a population is decreasing. G dash is in terms of hundreds per month. First up, sketching the graph of G dash of t. So this is tech active. We can just plot it on our axes and be fine. Only thing we'd have to be a bit interested about would be getting proper asymptote equations, not just eyeballing it off the graph, and figuring out the stationary points of the graph that we have. So let's crack on with it. First up, I'm just going to define the functions in our CAS, and we can get some information from there. Gx is equal to -3 bracket 1 minus t all squared e to the 1 minus t all cubed. Okay, that's the function that we care about. Just quickly double checking. Yeah, not seeing any typos. Cool. Then, to get an idea of what we're looking at, let's smack that on the axes. Fair enough. So we get a little dip going on there. We can clearly identify two stationary points that we need to find, and we can be reasonably certain that our asymptote is going to be x equals 0. You'd probably want to validate that on the math as well, just to identify why we might have an asymptote at x equals 0. Usually asymptotes are going to occur when we get undefined behavior. Label any asymptotes.
Chris, after you define the function, how do you go straight onto opening a new tab for the graph?
I didn't. I just went home and then graph.
Oh, okay. Yeah.
Yeah. Cool. From there, okay. Now it does say label all asymptotes. Technically, oh yeah, any asymptotes. Technically, it looks like there's a y asymptote here as well. A y asymptote of y equals 0. I guess you say the x equals 0 asymptote exists simply because it's also defined as t greater than 0. So maybe we're just not seeing enough. Maybe this does cross over, unless otherwise, because I'm not seeing anything in the math of the equation itself that would cause x equals 0 to be undefined, other than it just saying that t should be greater than 0. What if I chuck this all the way down to like -100? Yeah, okay, it does cross. So this is why I wouldn't want to use the graph as the be-all, end-all for what we're doing. But okay, so the only asymptote that's actually true in this case is going to be the y equals 0 asymptote. You can see that's definitely trending towards there. You can actually also prove it. Maybe I won't say that. How could we potentially prove what that asymptote would be? Or at least think about it in terms of the equation itself. What is it that causes a y equals 0 asymptote here?
No value of t will result in 0.
No value of t will result in 0, sure. What part of it is...
Wait, wait. No, it will be, there will be a 0 from what I can see.
There will be a 0. What causes a 0?
T equals to 1.
T equals 1. Okay. So,
Mhm.
1 take 1. You're going to have a 0 on the exponent, but what does e to the 0 give you?
1.
Yep. So, that's going to have a 1 there. Then from here, t equals 1. You're going to have 1 take 1 for 0. Oh. Wait, what? Yeah, no, that is going to give us y equals 0 as a value.
Yeah.
Why do they have it as an asymptote then? That's strange. Okay, this is... Yeah, nah. That's not great wording of the questions. I get the intention behind it was to label y equals 0, but that's not technically an asymptote where you actually reach it. Yeah, okay. Let's ignore that part then. So I guess we could just say there's no asymptotes, right? That'd be the true answer for this. No, good spot there. I got a little bit misled by the question. Anyway, the other part there is finding the stationary points of the graph. I'm hoping we're all quite used to how we would do that. How might we find the stationary points of this graph?
Derivative.
Yep, find the derivative, set it equal to 0. Let's go derivative of g equals 0, comma x. That's going to get us our two x coordinates. One of them is significantly stranger than the other. But we need the full point. We need both the x and the y, so all we're going to do is shove it back in to get the y's as well. G of all that nonsense. And while it is a nonsense answer, it is the, well, it does say correct to the nearest 100 rabbits, so lucky us, we get to evaluate that. Because it is a rate, we are allowed to have a negative number of rabbits, because it's not necessarily a negative number of rabbits, it's a decreasing in the population. Remember, we started with a derivative graph that was talking about the rate of the change. You'd also give the x value as well as the oh, they're the same thing. Did I click the wrong thing there? Yeah, I must have. Yeah, okay, I was going to say. You'd also give that as the other one as well. Cool. Okay, then from there, endpoints. So we knew t greater than 0, there's an endpoint there, so just whatever g of 0 is, you'd give that as well. As an open circle thing. Any questions there? We got our stationary points, endpoints, and all weird discussion on the asymptotes. I don't think they intended to actually have it equal 0 at any point. If there's no further questions, have a look at part B. By how many rabbits did the population decline in the first 2 months? So how many were actually lost? That's a cool question. T is in time, T is in terms of months, so we don't have to worry about any unit conversions there. There is definitely one thing to worry about the wording of here. By how many rabbits? That's going to play a role in how we think about or solve this question. And it's a lesser tested concept. You can do this a couple of ways.
So I'm looking at the last part of this then. So where t is time in months, t greater than 0, and g dash is the number of hundred number of rabbits in hundreds per month. Does that have to do with something?
There was an audio thing in the middle of what you said. Could you repeat that? Sorry, it kind of cut you out a bit.
So it's the last part. G dash, the number of rabbits in hundreds per month. Does that have to do with it?
Yeah, that's right. So G dash is G dash is the number of yes, exactly. So relating that directly to what's being talked about now. I think, yeah, that's going to be the number that is declining or increasing depending on what it is. Yeah. But it's a rate. So that's in terms of the rate at which they're decreasing. I'm going to have to, I think, reword this entire question, because their intention was to say G dash is the rate of rabbits decreasing. More so it's G that's the actual raw numbers themselves. Same thing with this here.
Do we have to do anything with... well, there's obviously integration going on from what I can see, but...
There is, absolutely. What are you spotting that requires integration?
So it's the amount of the number of rabbits lost.
Mm-hmm.
So like maybe the area between the graph and the x-axis and multiplied by 100.
Yeah, because it's rabbits per 100. Yeah, that's exactly what it is. That's the fastest way of doing this, which is going straight to the integral itself. What's the boundary on our integral going to be?
Uh, 0 to 2.
0 to 2, because it's from month 0 to month 2. That's exactly what it should end up being. Now that's going to give you, in terms of the decline, which is why it's negative, you're obviously just going to flip that to being positive and multiply by the 100 for 235 there. So the reason why area bound between the curve from 0 to 2 worked was because during that process you're anti-diffing from the rate equation to the actual equation which has the raw numbers of the thing. It's like having a volume equation and diffing that down to the rate of loss of volume, for instance. You want to get back to the thing that actually has the unit you care about. Now, I think this dash shouldn't be there in the actual question to be a bit more clear with that. Well, maybe it does actually, sorry. It wasn't just rabbits per 100, it's also per month. Yeah, never mind, they did have it right. I just didn't read this last bit. So you want to get it back to the thing that actually has the unit. And when you do that anti-diff, that's what you're doing. Putting it between 0 and 2, what you're essentially doing is capital G of 2 minus capital G of 0. Or in other words, the rabbits at month 2 minus the rabbits at month 0. So the math is supporting that gets you the difference in rabbits from month 0 to month 2. You're just doing it via one step rather than 2 steps of thinking about, okay, I'm going to integrate it and then I'm going to do the equation. What you'll find is the math is identical. Area between the curve from 0 to 2. This is the last point in integration calculus, which is they say, okay, what does area under the curve mean? Well, here's one application of it. It could mean the number of rabbits that were lost from 0 to 2. It could be the amount of volume of liquid that was lost from whatever or whatever. Depends on the function descriptions. Alright, that's about it there. If there's any further questions about this or anything else, happy to answer them. Otherwise, that's time. Thanks, guys.
Thanks. Have a good day.
Thank you. You too.
Hey Chris, I just wanted to ask about bound reference.
Yeah.
Like, if you had any advice for that.
Say again.
Like, if you had any advice for bound reference?
Any advice for bound reference? So basically, all of the modules in the school that I've written up, I've made them in a way where you can, if that's a topic that you're struggling with or whatever, you can just print that off and put it directly into a bound reference.
Yeah,
Now-
I was just about to ask that as well.
Yeah. Now, whether you want to print off the whole thing or just a summary at the end is going to be up to how much detail you want. You don't lose anything by printing off the whole thing, except I guess printing money.
They don't care how like big it is. Right?
No, I think I've shown several times on these how thick the book I had was. It's probably like, probably the size of my head actually in terms of thickness. The book.
I mean, you can never have too much, to be honest.
Yeah, it's just a fat spiral bound book of just everything.
Is it really that useful? Like at the end of the day, like
I mentioned this a couple of times before. In the actual exam that I did, in exam 2, I think I opened it once, and that was just to quickly check up on a formula that wasn't on the formula sheet. Didn't really care to look for any work solutions, any explanations on concepts, because you don't want to be teaching yourself concepts in the middle of the exam. So if you're doing it for that, then, I mean, yeah, it'll get you the mark, but it'll also probably be not as time efficient as just doing what you already know and then going on from there.
But if it's like you're not, like for stuff that you don't know that well, like it is helpful.
Yeah, because it'll help you get the answer for it. Absolutely.
Yeah. Yeah. Obviously, the timing is hard.
Yeah. So the main advice is always going to be just do all the questions that you're confident in. As soon as you run into any pressure at all or any resistance in the question, you're trying to think too hard, move on to the next one. It's only once you've exhausted all of those that your bound reference might come in handy to help you out with certain things. I think the bound reference is more so going to be for peace of mind than any actual utility itself. Again, I only used it once in the exam, and I didn't exactly score a perfect score. So there was
obviously it depends on like where you're at as well.
Yeah. It'll have varying degrees of utility depending on where you're at. Absolutely. And so depending on how much detail you want in there, or I guess how much printing money you got. I would personally just print it all off into one big thing. Try to put put it all in one big PDF so you can have it numbered and chaptered out.
Yeah.
It does get pretty big, so you definitely want to chapter it out if you are going to print it all off. Otherwise, I've also created the summaries, which is just the bare bones stuff you need for any given chapter. Like, you might not print off your linear at all. Like, does anyone really need a refresher on linear?
No.
You probably don't need that. So, pick and choose what you want in there. Also, it's perfectly fine if you just want to print off the whole thing as well. It's whatever you want out of it.
Yep.
Cool.
Because we're just in revision now because we've pretty much finished it.
Well, yeah, because we've done all the calculus stuff up until now, and I realised I was looking at you guys' planners, and I'm like, shit, you guys are doing the calculus SAC like this month, and you're doing the integration SAC next month, and I'm like, well, we've kind of already covered all that. So in class 2, it doesn't make any sense to look at probability yet, unless you guys really want to. But
no, I think I'd rather just
I well and truly gave you guys heaps of SAC prep time, and we have a lot to look at. But
I'll probably send in a couple questions for integration.
Any of the class 2, class 3.
Having some problems with integration and applications of integration.
Yeah, well, here's one of them right here. Application integration. But absolutely, in this SAC period of time, unless anyone sends me anything, I'm just going to go through all of these, and we'll take it from there. So send any questions in, any and all of them. Happy to do a full lesson on
you could like screenshot like specific questions as well.
Yeah. As in what you're saying, you're going to screenshot some and put them in the Google form.
Yeah, can I do that?
Yeah, that works. There's a spot to attach images.
Oh, okay, cool. Yeah, so I just wanted to check.
Yeah.
Awesome. Sounds good.
Easy.
Cool. Thank you, Chris.
No worries.
Have a good night.
Have a good night.